Hello and welcome to Unit 2, Lesson 5, Common Sense. We have a lot of reading here, but basically our goal is to use logarithms to solve exponential equations. So let's begin. You already know our number system is base 10, right here. So that each of the different place values in a number are powers of 10. That makes the base 10 exponential and the base 10 logarithmic functions very important. Because the base 10 logarithm is so commonly used, it's called the common log. And to make the notation a little more compact, it's generally written without the base. So it's used like this. See how the base is just assumed to be 10 when a base isn't written? This is the kind of concise notation that mathematicians just love. When you use the log key on your calculator, it's automatically base 10. Each of the sections below contains puzzles for you to solve about base 10 exponential functions. You'll be using base 10 logarithms and your knowledge of exponents to find missing values for exponential functions in tables, graphs, and equations. As you're working, watch for strategies that will help you to solve equations that have a variable in the exponent. All right, so here's some missing values in these tables. And you might want to pause and see if you can figure out some of these missing parts. Okay, we're back. How did you do? Well, one that might have been easy for you was 2 right here. But what about 50? Well, it's not so obvious. This is 1.699. Now, how did I figure that out? Well, I knew that if I take the logarithm of the numbers on the right side, I'll get the numbers on the left side. So this is basically log of 50 right here. Now, what about on the other side? Well, this one's -1. How do I know? Well, let's work it backwards. 10 to the -1 is 1/10, and then 3 times that is 3/10. Okay, but I had to start by knowing that it was -1. Not really fair. And what about this one that's 94.87? Well, that actually turns out to be 1.5. How would I know that that was 1.5? Or that the last one was 2.7? You might be thinking, this puzzle is not fair. Well, let's continue. You'll see that we can make it fair. When you were trying to find x when y was 50 in the first table, you were probably thinking of an equation like 50 equals 10 to the x. Even if you didn't write it down, here's your chance. Write all the equations and their solutions that were used to find the missing x in both tables. I give you the first ones, and you're welcome. So let's see. Table A. How could they have solved it? More to come. But you know that second equation, well, if it follows the pattern, would have been something like 100, let's highlighter. 100 equals 10 to the x. In the other table, the first one would have been 0.3 equals 3 times 10 to the x. Do you see the pattern yet? The next one is 94.87 equals 3 times 10 to the x. And the last one, 1503.56 equals 3 times 10 to the x. So the pattern here is that the expression for the function is equal to the output that you're looking for. That would be the strategy, number 2. Number 3. Here's the graph of 10 to the negative x. Use the graph to solve the equations for x and label the solution. So what you would do here is look for the y value being 40. And so these graphs are separated so that every minor line is worth 5. So we get to the middle, we're at 25, 30, 35, 40. There's 40. You go over to the graph. Then you look straight down. And let's just estimate that. It's about negative 1.6. Because every major or every division here is worth 1. This is 1, 2, 3, 4, and then 5. So that would be A. B is 10. Let's see, 2 markings up. That would be right here. That's on negative 1. And 0.1 is so very close to the axis. It's hard to tell if it's 1 or 2 or 3 or 4 or 5. We're going to put 1 because you can work the problem backward, and 10 to the negative 1 is 1/10. So that would be here. Okay, let's look a little closer at the solutions. Consider this equation right here. Would you get the same result if you took the base 10 logarithm of both sides? Try it here. So we're pushing the log onto both sides. And this one on the left is going to turn out to be negative x. And this one on the right is going to be 1. So if negative x is 1, then positive x is negative 1. Let's try it again for this next equation. Apply the log to both sides. And I don't have to write the base, but they did on the previous problem. Let's see, we'll write it like they did, 0.1. So this is negative x over here, and this is negative 1. Nope. Let's try that again. The log of 0.1. Yeah, that's right. It's negative 1. So positive x is positive 1. Why does this process give the same value as the graph? Because logarithms, let's try this again. Logs are inverses of exponentials. So we're undoing around x to solve for it. Let's see, 7, one of the equations you wrote is right here. How could you unwind this equation? Okay, so what we're going to do first, I divide by 3. 31.623 is equal to 10 to the x, and then we apply the log to both sides. And that goes on forever there. Log base 10 of 10 to the x is just x. And that was about 1.5. Now you're ready for the equation puzzles. So here we go. Apply the log to both sides. This is x, this is equal to, and this is 5. Oh, not 5. 4. Count the zeros. 1, 2, 3, 4. Okay, this is log 125. Log of 10 to the x. Log 125 equals log 10 to the x. So I have to put this in the calculator. Log of 125 is x, and that will be 2.1. Let's see, how many decimals am I supposed to go for? Doesn't really say here. Now this next one, it's got an extra step in it. We're going to do the log on both sides. Okay, we're going to, well, actually, that'll inverse itself, just giving us x plus 2. And that's log of 347. Subtract 2. Now remember, order of operations says we got to do the log first. So I'm going to type in log of 347, get the answer to that, and then subtract 2. So we should be getting 0.54. First divide by 5. So 10 to the x plus 2 is 0.05. And then we'll take the log of both sides. So x plus 2, log of 0.05, we'll subtract 2. And again, remember to get the answer to the log first, and then subtract 2. So I'm just going to start by taking the log here. This will be negative x minus 1, log of 136. Add 1. So negative x is log of 136 minus 1. And finally, oops, let me erase it. Finally, divide by negative 1, the whole thing. So on a calculator, make sure that we have evaluated the top of the fraction before we divide by negative 1. So that would be log 136. It's about negative 1.55. Subtract 1. Now I'm at negative 2.55. And then divide by negative 1. And it's about 2.5563. So let's say 2.56 approximately. Okay, 13 is going to be no solution. This negative means negative 1. If we divide by negative 1, that means 10 to the x plus 2 is negative 16. As soon as we apply the log to both sides, the log of negative 16 is a domain error. It's undefined. You cannot put a negative number into a log. Therefore, this has no solution. Or in other words, the solution is the empty set. So here's another way to say it. X belongs to nothing. All right, these combo puzzles, you can do this as a graph, or you can do it by setting the right sides equal to each other. If you do this by a graph, like for example, you can use Desmos. You're going to get 100 here. You're going to get about 1.875, comma 25 here. And you're going to be getting negative 0.64, 4.36 here. So definitely, if you had access to Desmos, put those in and you'll find a solution. Now, on the ready for more, what if you're not in base 10? So it says here, method 1, use a base 2 logarithm to find an exact expression. So if you go log base 2 of 2 to the x minus 1 equals log base 2 of 30, then this is x minus 1 equals log base 2 of 30. And you can add 1 to that. There's your exact answer. Although, according to the book, they haven't given you a way to evaluate log base 2 of 30 yet. Okay, method 2 will give you an approximate value. So if you do the log base 10 of 2 to the x minus 1, then that will be equal to log of 30. Then I can take this and bring it out to the front. X minus 1 times the log of 2 is the log of 30. Divide by log of 2. X minus 1 equals the log of 30 over the log of 2. Please don't write that as the log of 15. That's not how the property works. And if you add 1, this is something you can type into a calculator. You're going to get about 5.91 when you do. So some strategies and the takeaways. Always use estimation. You should be getting answers that make sense. So estimation, always in play. Then what do? We took the log of both sides. You want to leave as much as you can in your calculator. In other words, you don't round off in the middle of a problem. You'll always round at the end. Always round at the end. Some equations can't be solved easily algebraically, so you can solve graphically. And that means looking for a point of intersection. And how you would do that, y equals the left side of the equation, y equals the right side of the equation, and then you look for something like this. The place they cross, the x value is what? All right, that'll do it. We'll see you next time.